Okay, in this video on Laplace transforms, we will learn about, we'll do a review of differential equations, a review of complex numbers, and then we'll get into the Laplace transform, what it is. We'll talk about the time domain versus the S domain. We'll talk about the important properties of Laplace transforms that we're going to be using. We'll talk about the inverse Laplace transform and how to solve ODEs using Laplace transform and inverse Laplace transform. So at the end of this video, you should be able to understand and apply the Laplace transform and be able to solve ODEs using it. So let's suppose we have a general input-output ordinary differential equation. So this is what we've been trying to get. This is our model. So we found out how to find these differential equations for mechanical, electrical, and fluid systems. The time response, so if I put in x of t, the y of t function that I get out is going to be like this. It will look like this. It has two parts, a particular solution, yp, that's the steady state solution, and a homogeneous solution, which is the transient solution. So there's going to be 4 steps to getting a solution to this, to finding this function y of t. First, we have to solve for a particular solution, yp. Next, we solve the homogeneous solution, yh. Then we add the two together to get the total solution. But at this point, we're still going to have some unknown coefficients. So we can find those unknown coefficients by matching up initial conditions. Let's do a simple example, a first-order system. So this is the type of equation that you have for a thermocouple when you model a thermocouple output. So first of all, here's the standard form. We have tau times derivative of y plus y equals kx. Tau is what we call the time constant of the first-order system, and k is what we call the static sensitivity. So we'll take a look in this example at a step response. So we're going to change the input immediately, and then we're going to see what happens to the output. So for a thermocouple, that time constant would be about 1/10 of a second, and the sensitivity would be about 5 millivolts per degree Celsius. So when the thermocouple is at room temperature and it's settled out, the temperature in the room is 25 degrees Celsius, and then it suddenly changes to 80 degrees at time 0 seconds. What will the response of the thermocouple be? Okay, let's go ahead and plug in those numbers. There we plug in for tau and for k. All right, now let's try to find the particular solution. Okay, the input is just a constant temperature level of 80 degrees Celsius. It turns out that the particular solution always looks like the input. If you put in a constant, you're going to get a constant out. If you put in a sinusoidal function, you're going to get a sinusoidal function out. If you put in a ramp where you continuously increase the temperature, then the output of the thermocouple will continuously increase. Okay, so we suppose that it'll be a constant. Now let's try to find out what the exact value of that constant is. So we'll substitute it into our differential equation, VSS, and solve for that value. Okay, at steady state, the derivative is a constant, so VSS doesn't have any component of time. That means that's 0. Okay, and it's very easy to solve that VSS is just equal to 0.005 times that 80 degrees Celsius, and that's going to give us 0.4 volts. All right, that's the particular solution. Let's solve for the homogeneous solution. First of all, take the input and set it to 0, and then find out what you have. Okay. So the homogeneous solution, the easiest way to do this is to basically know the answer already. Let's suppose that the homogeneous solution looks something like this. Actually, it always does look something like this, or maybe a few more terms. But for a first order equation, it looks just like this for an ODE. All right, let's plug that into the equation. Right? If I have YH, I can plug it straight in here. So let's take the derivative of y of h. Well, that's actually pretty easy. It's tau times lambda times a e to the lambda t, and then plus I plug in the a e to the lambda t for yh, and set that equal to 0. All right, I can factor that, okay, into 2 halves, tau lambda plus 1 times a e to the lambda t. Now you'll know that the exponential is never 0. Okay, so that right part of that right factor cannot be 0. The only thing that can be 0 is this right here, tau lambda plus 1. So we can go ahead and set that equal to 0, and we can solve for what lambda must be. Lambda must be -10. All right, so there we have our homogeneous solution. Okay, but you see there's still a constant. Okay, so we'll have to figure out how to what the value of that constant is. That's going to be the next part of this. I would like to draw your attention to this equation right here. Right here. This is what we're going to call the characteristic equation, and it's going to be very important for later on, even after we no longer use, even when using Laplace transforms. The characteristic equation will be very important. Our total solution, just adding the two halves. All right, let's try to match the initial conditions. So at time t equals 0 seconds, what is the output? What is y? Well, we know the input was 25 degrees Celsius. The output will just be the static sensitivity, just like before. So it's going to be 1/8 of a volt. Okay. Now, yt equals dss, that was our particular solution, plus ae to the lambda t. All right, so plug in those values. All right, let's plug in 0 for time. Okay. All right, now we have 0.4 plus ae to the 0. So that'll just be a, because e to the 0 is 1. And we can solve for a. All right. And finally, we have the total solution. So the 0.4 was the particular solution. We solve for a finally. We solve for lambda, and we solve for a to find the homogeneous solution. And now we find that y of t is equal to that equation in volts. Okay. Let's go ahead and plot this out. What does this look like? Just like that. Okay. It's going to start at 0.125 at time 0. It's going to end at 0.4 at the final time. Sorry. Let's analyze this a little bit. It's equal to the particular steady state solution, okay, which looks like that, and plus the homogeneous solution, which if you plot out that function, it looks something like this. All right, you notice it's negative, right? A with a negative number, so looks like this. Let's add those two together, and you get that final solution. Okay, so what we've just done is we did this approach. We had differential equations, we had initial conditions, we used calculus to find the solution in the time domain. What I'm going to show you in the next video, because this one's already getting a little long, is when you can take a Laplace transform, your differential equations become algebraic equations. And using algebra, you can find a solution in the Laplace domain, the S domain, what we'll call it. And then using the inverse Laplace transform, you can recover the solution in the time domain. Okay, so we're going to have 3 steps, which are not too difficult, to replace one step, which is fairly difficult. All right, last thing for this video is I'd like to review complex numbers. Okay, so imaginary numbers, if you will, but complex numbers. You're probably familiar with this form of a complex number where we have x and y. We have z equals x plus jy. J and I are both the square root of -1. I'll use both probably in this class. But, all right. So let's take an example of z equal -5 plus j4. We can plot that on the imaginary axis just like this. Okay, so here's where you'd plot z. Okay, here's x. All right. The real component is negative, and y is the imaginary component. Okay. Now there is another way to look at this number, okay, and that is in phasor form or Euler form. Okay, and we use this: z equals a times e to the j phi. All right, and we call this a the magnitude and this j the phase. All right. Now if you use Euler's formula, basically Euler's formula tells you that this e j phi is equal to cosine of phi plus j times sine of phi. So how do you convert between these two? Like this. x and y, do a little trigonometry, you find a cosine phi, y is equal to a sine phi. And how about the other one? Going to phasor form, this is a little more tricky, but using a little more geometry, a is just going to be, the square root of the squares. And phi, you actually need to use arctangent. Now I've used here a tan 2, okay? Because you need to use a coordinate sensitive phi. You notice that my phi here is not, it's more than 90 degrees, okay? So you need to know that it is in the second quadrant, not in the third quadrant, or the third quadrant, like it might like you might get from your calculator. Okay, so when z is in the second quadrant, you need to add 180 degrees. Okay, so just keep in mind what number you're expecting. Okay, all right, so that's important. And there is a command in MATLAB called atan2. All right, where you, instead of putting in y divided by x, you put in y comma x, and it will give you the proper coordinate, the proper quadrant. Okay, that's enough for this video. And in the next one, we're going to cover the details of what the Laplace transform is and how to use it. This is just good preparation.